Back. We started the last unit and we discussed the RC phase shift, right? In the RC phase shift or in the oscillator, the foremost condition is A beta should satisfy this condition. Means A beta multiplication of forward gain and backward gain beta should be equal to 1 and the phase angle between them would be 0 or 360 degree. Is it okay? This is the foremost condition for any oscillation, right? For A beta equal to 1 only we'll get the sustained oscillation. Okay. Then we have seen the RC phase shift. RC phase shift. In the RC phase shift, we seen the formula for frequency was 1 by 2 pi RC under root 6. And the RF was 29 times of R1. This was the condition for RC phase shift. Now we'll see the Wien bridge oscillator. This is totally based on frequency setting. Okay. So let me show you diagram. Okay. The circuit diagram. Exact circuit diagram for the Wien bridge is this is the op-amp circuit to get the forward gain. Let's take it Rx and this Rx is variable. Here it's R, it's grounded. Output stage, obviously it will be positive feedback, and here the circuit is like this. Okay. CR, and here in parallel CR. It's like this. This is your Wien bridge. Okay. So friends, in this circuit you can draw it in the form of bridge also. That's why we are calling it bridge, right? So in the bridge, if you'll draw this, in exam also they can ask in this way also. This is Rx variable. Over here in this branch, the resistor and capacitor, they are connected in parallel like this, C and R, and this is the branch of R like this. Okay, and the op-amp is connected between these 2 points over here like this, and this is the non-inverting terminal, inverting terminal. This is the bridge structure, and this point is grounded. Okay, this is the Wien bridge structure. See, if we'll take points over here A and B, so this point is A, and this point is, we have one point over here also. The point is connecting, this is B point, this is C point, and this is grounded over here. Now you can see with the A and C, both are connected. Between A and C, at the C terminal, the non-inverting terminal of the op-amp, and A is the inverting of op-amp. With this A, R is connected to ground. With this A, R is connected up to ground. With this A, Rx is connected up to point B. From point B to point C, this series CR branch is connected over here, perfectly fine. And at C, this C, the parallel branch is connected up to ground. So this is equivalent of this. Okay, this is Wien bridge diagram. So this is audio range. Actually, this is the audio range oscillator. Okay, means up to 20k kilohertz we'll use it. Okay. Now in this circuit is going to provide 180 degree phase shift. This circuit is going to provide 90 degree phase shift, and this is also 90 degree phase. And we know the C and R sharing 90 degree phase shift itself. Okay friends. Now after this, what is our task? Our task is to find out A and beta. This is VF, this is V0. For A, you need to take V0 by VF, and for beta, you need to take VF by V0. Is it okay? A is simple, given over here. It will be 1 plus Rx plus R. Yes, this is the C. The input is provided to non-inverting terminal, so gain is 1 plus Rf by R. Okay, so A is clear with you. Rf by R plus 1. A is clear. Now we have to calculate what? VF by V0. See, this is the circuit. So can I arrange this circuit in this way? Let me show you the circuit. In that circuit, 1 by CS connected parallel with R, and in this branch R is connected parallel with 1 by CS, and over here I have V0. This is the output branch, and over here I have to calculate VF. Now you have to calculate, or you have to come with the relation between VF and V0. So what is voltage over here? Voltage over this is VF. So this VF is equal to this R into this V0 divided by summation of this. R plus 1 by CS plus R, like this. So when you will come with the relation, what you will find? You will find beta is equal to, let me show over here, beta equal to, you will get SCR divided by SCR whole square plus 3SCR. This will be your plus 1 also. This will be your beta. You have already find out the AF, and AF is 1 plus Rx by R. Now what you will do next? The next condition and the foremost condition for sustained oscillation is A beta should be 1. So this beta, again you can rearrange it. SCR will take out. So it will be in denominator SCR plus 3 plus 1 by SCR. And you will replace SC by J omega. So you will get, final I'm telling you, you will get 1 by 3 plus J omega CR minus 1 upon omega RC. This will be your beta. Now you are going to multiply this beta with 1 plus Rx. Okay. So A beta should be equal to 1. This is our condition. So I need to multiply this beta with A. Definitely. And the A is 1 plus Rx by R equal to 1. Is it okay? So if you observe this, this is the condition. So this denominator will go this side. So it will be remain with Rx by R equal to 3 plus J omega CR minus 1 upon omega CR. Now we have to equate real part to real part, imaginary to imaginary, both the sides. So here the real part is equal to 3, definitely, because this entire is the imaginary part. So real part is given 1 plus Rx by R equal to 3. It means Rx by R should be equal to 2. It means for sustained oscillation, the foremost condition in when bridge is Rx should be 2R. Okay friends. What about the frequency? Omega CR is coming. Omega CR. So in this case, we are getting omega is nothing but 1 by RC we are getting. Okay, because this omega square CR, everything is given. So finally we'll come with omega equal to 1 by RC. If anyone will ask what is the frequency, so frequency in hertz is 1 by 2 pi RC. Perfectly fine. This is condition 1. The condition 2, the Rx or the RF should be equal to 2 times of R. This is the condition for Wien bridge. And the condition for RC phase shift, again, the omega was 1 by 2 pi RC with additional root 6. And earlier I told you how to remember this. In the second, this was the first condition there, and the second condition was Rx or Rf should be 29 times of R. Is it okay? So we'll discuss each and every oscillator, and at the final we'll come out with these two things only, the Rx and the frequency. Sometimes they'll frame the question around this, and sometimes they'll ask the question directly around this concept. Is it okay? Now, so we have seen earlier that Wien bridge is using for audio range. Is it okay? It means it makes 20k hertz. And the RC phase shift we have seen earlier. This is the RC phase shift. It was in kilohertz and something we were using. So remember this point that RC phase shift and Wien bridge, they are used for low frequencies only. Very low frequency. For the higher frequencies, their performance is very low for RC. So for higher frequency we'll go to LC. LC oscillator we will see. We'll see LC oscillators, in which we'll be having only inductor and capacitance. Okay friends? Now let's see what is the theory part of Wien bridge given over here. The Wien bridge oscillator is a standard oscillator circuit for low to moderate frequencies. Okay friends? In the range of 5 Hz to about 1 MHz. This is highest, 10 to the power 6 MHz. But in practical we were using up to 20 kHz only. Okay? It is mainly used in audio frequency generators. At very low frequencies, the series capacitor looks open to the input signal and there is no output signal. At very high frequencies, the shunt capacitor looks shorted and there is no output. See, this is the condition. What is going on? If omega is equal to 0, there is no output. Why? Because this thing will be open, there will be 0. If omega is infinity, definitely it will be short circuited. This one also short circuited. And if this is short circuited, the ground is directly connected to V0. So in both the cases we are getting 0. So Wien bridge is not suitable for lower frequency as well as higher frequency. So it is suitable for the moderate frequency. Because we have seen this. At very low frequencies, the series capacitor looks open. This is the series capacitor. It will be look open. And there is no output signal. At very high frequencies, the shunt capacitor looks shorted and there is no output. In between these extremes, the output voltage reaches a maximum value. The frequency at which the output is maximized is called the resonance frequency. The resonance frequency, okay? At this frequency, the feedback fraction reaches a maximum value of 1/3. Okay friends? Means the feedback whatever is coming, it will be 1/3. When the frequency, see, at the resonance frequency. Okay, and the resonant frequency is the frequency where the voltage reaches a maximum. I hope it's clear to you. You can see over here. The gain is going to increase because at 0 also, omega equal to 0 also 0. At omega equal to infinity also it's 0. So it's going to increase again after this 0. Again increasing over here, but up to some point only. At that point is resonance frequency. FR, resonance frequency. At this frequency, the gain is max, I can say. The maximum gain you will get. Okay? And this is 1/3 of the total. What it means, see. This equation shows that the maximum value of gain occurs at Xc equal to R. When Xc equal to R, then only maximum this gain occur. Okay? And phase angle also becomes 0. So this represents the resonant frequency of load leg network shown in the figure. See over here, you can see. Just remember for this that at the resonant frequency we are getting maximum output voltage in case of Wien bridge. I think it's clear to you. Okay friends. So we are getting 90 degree at omega equal to 0. And here we are getting minus 90 degree. So total we are getting 180 degree phase shift. Correct? Now come to this circuit we have seen earlier. Shows a Wien bridge oscillator. The operation amplifier is used in a non-inverting configuration. Definitely, no problem. And the lead leg network provides the feedback. So this network provides feedback, right? Now resistor RF and R1, here are the resistance RF and R1, determine the amplifier gain and are selected to make the open loop equal to 1. Okay. If the feedback circuit parameters are chosen properly, there will be some frequency at which there is zero phase shift and the signal fed back to non-inverting terminal. Because the amplifier is non-inverting, it also contributes zero phase shift. So, the total phase shift around the loop is 0 at that frequency is required for oscillation. We discuss about this. If we are getting 180 degree over here, it should provide 180 degree again. So overall, it should be 360 degree or 0. Okay? Okay, fine. Now the oscillator uses positive and negative feedback. Both are connected over. So the positive feedback helps the oscillations to build up when the power is turned on. Is it okay? And after the output signal reaches the desired level, the negative feedback reduces the loop gain is 1. The positive feedback is through the lead leg network. The positive feedback is through the, see, this is the lead leg network. Okay. The positive feedback is through the lead leg network to the non-inverting input, and negative feedback is through the voltage divided to the inverting input. Okay friends? Now we reach to the LC phase shift, means LC oscillators. LC oscillators, okay? So we'll see first the general configuration of this, okay? The LC oscillator circuit is like RF over here connected like this. Definitely here I'll have R1 like this. It will be like over here Z3 and Z1, Z2, and this one is grounded. Okay, this is the generalized configuration of LC oscillators or LC phase shift, I can say. See, this is the inverting terminal. It will provide inverting amplifier. It will provide 180 degree, and this is split tank. This is we call split tank. This tank will again provide 180 degree. So total will get 360 degree. Okay. Now the question is how to solve this. See. So out of these 3 impedances, 2 will be, or the totally will be L and C. Is it okay? So based on the collection, here we are having only 3. So we can keep like inductor, capacitor, or capacitor, inductor. We have only 2 possibilities over here. So that's why the LC phase shift or the LC oscillators divided into 2 categories only. We will see later. Before that, we have to understand this split tank. Wait a minute. So in this split tank, if you find out, There is no current in this circuit because op-amp do not take any current. No, there will be current in the circuit because op-amp branch is this branch. Okay. So suppose we are considering only the split tank. How the split tank is going to do? What is the application of this? See, over here the situation is like this. Okay. So this is V0. Okay. This is VF. No problem at all. This is VF. This is V0. This is grounded. In this the current is this. Let's take the current is this, suppose. What will be the current over here? In this, can I take this current is nothing but V0 by Z2? Can I take the potential difference V0 minus 0 divided by Z2 is the current? Right? Or the same current is nothing but 0 minus VF. 0 minus VF divided by Z1 also. The same current. See, current I is over here means 0. Here the potential is 0 volt minus Vf divided by Z1. Okay. So these two are equal. Means we have V0 by Vf equal to minus Z2 by Z1. Okay friends. So if we talk about beta. Beta is what? V0 by Vf is A. This is nothing but A. So in terms of A, if we'll talk about, A is nothing but minus Z2 by Z1 we'll calculate directly. Is it very easy to calculate? And someone will ask what is the beta? So inverse of this minus Z1 by Z2 will be beta. Now what is the condition? Condition is A beta equal to 1 at an angle 0 we have to keep. So this is the generalized configuration. Now we'll see the two categories of LC oscillators. Okay friends. So let me take on the fresh page. Okay. Wait a minute. Okay friends. So we have seen that over here beta we got minus Z1 by Z2. Perfectly fine. No problem at all. So this minus sign, can I write it like this is Z1, Z2 providing 180 degree phase shift? Yes, I can write. Similarly, A we are getting minus Z2 by Z1. Here also I can write Z2 by Z1 and phase shift is 180 degree. So total phase shift is 360 degree over here. Okay, but my intention is now I have to show you two categories of LC oscillators. Two categories. So three things we have: Z1, Z2 and Z3. Okay friends. So based on the selection of this, we have two categories. Number one is Hartley. Hartley oscillator, Hartley LC oscillator, or you can say, and second one is Colpit oscillator. Okay friends. Two categories, Hartley oscillator and Colpit oscillator. If you have Colpit oscillator, then your Z1 and Z3, what we are choosing over here in the circuit, Z1 and Z2. Yes, Z1 and Z2 will be capacitors, but Z3 will be inductor. So what I'm saying is, if you will see the Colpit configuration, C is given over here, so you can remember you will be having two capacitors over here. So obviously if you consider two capacitors, the remaining one will be inductor. And Hartley oscillator, the L is coming over here, L. So you can remember by this, Z1 and Z2 will be inductors. Okay, and Z3 will be capacitor. Is it okay? This doubt is clear to you? Now let's come to the Hartley and Colpit. Okay. So let's consider first Hartley oscillator. Okay. For the Hartley oscillator, the Z1 is inductor having L1 inductance, Z2 is L2 and Z3 is capacitor. Okay. And here beta we have found minus Z1 by Z2. And A, if I'll talk about in terms of forward, because the circuit was given like this, RF and R1 is also given. So in terms of this RF and R1, this A will be minus RF by R1. Okay. If at the non-inverting terminal you have input, suppose, so you'll get minus RF by R1 as your gain. And in inverting terminal, in non-inverting terminal, you will get R1 plus RF by R1. So this is the this is the inverting, so minus RF by R1. Beta is minus Z1 by Z2. So what is Z1 over here? L1. See, this is the impedance, okay? So when you will convert it into impedance, it will be SL1. This will be SL2. And this will be 1 by SC, like this. So if you keep the values minus Z1 and Z2, you will get SL1, SL2, SS will cancel out, will remain with L1 and L2. Okay friends, this is the L1 and L2. Now your condition is A beta should be 1. So beta is minus L1 by L2 and A is minus RF, so minus will become plus RF by R1 equal to 1. So from this equation, RF by R1 equal to L2 by L1. This is the condition for Hartley oscillator. It's very simple, right? For Hartley oscillator, the condition is RF by R1 should be L2 by L1. In this condition only, you will get A beta equal to 1, or in this case only, you will get sustained oscillation. Okay friends? So, RF by R1, you can remember this in this way. This RF is nothing but R2 kind of thing. This is R1 kind of thing. So R2 by R1 equal to, if this is 2, so this is to L1. Is it okay friends? I hope it's clear to you. Now come to the culprit. Okay. Now Hartley is completed. Now we'll see the culprit. Okay friends. Wait a minute. The culprit now. So in the culprit, the Z will be capacitance C1, let's take. Z2 will also capacitive and Z3 will be inductive. Okay. Again, the beta for the both the thing is minus Z1 by Z2. And A for both is minus RF by R1. Perfectly fine. Now, what is minus Z1? It will be minus 1 by SC1. What is Z2? 1 by SC2. So, C2 will go up. So, it's a C2 by C1. Okay, this is your beta. Now, Barg-Hassan criteria. A beta should be 1. So, A beta should be 1. It means, let me erase some part, then I'll show you. You are getting minus C2 by C1. Your beta is minus C2 by C1. Your beta is minus C2 by C1. So this is C2 by C1 multiply with A minus RF by R1 equal to 1. Minus become plus. So finally you have C2 by C1 equal to R1 by RF. Is it okay friends? So this is the condition for culprit oscillator. For the culprit, the condition is RF by R1 is equal to C1 by C2. And for the Hartley, the condition is RF by R1 equal to L2 by L1. Okay. Now I'm telling you easy method to remember these two things. See, what is the time constant in terms of R and C? It's RC. What is the time constant in L and R? It's L by R. Is it okay? So see, I'll convert this RF into C2. The C2 will go to this side and this will come to this side. This is R1 C1. So this is the kind of time constant. So remember like this. This is the time constant of the output and this is the time constant of input. So this thing will fulfill over here also. So for Colpit and Hartley, you have to remember Z out will be equal to, tau out means time constant, output time constant will be equal to input time constant. And time constant, if RC you are considering, Colpit you have, so definitely the RC. If you have Hartley, so you will use L by R. So in this case, L by R, let's make L by R. See, here is, this is L. So this is L2, here the condition is L2 by RF. And L2 by RF and L1 by R1. See, over here also the situation is same. Output time constant equal to input time constant. Okay, friends. So these are the conditions. So till now, we have seen total how many? 4, right? First, we have seen RC phase shift. In the RC phase shift, the frequency formula was 1 by 2 pi RC under root 6. How to remember this? I told you earlier. This is R. Make it like this. This is 6. So this is under root 6 in denominator. Perfectly fine. Now RF is 29 of R1. So to remember this 29, again you can take over here from this R. If you remove this, so it will remain with 2 and you have to make it, this is 29. So this is the 29. Okay. So RC is over. Next, after RC, we have seen Wien bridge. In the Wien bridge, the frequency was very simple, 2 pi RC. Okay. And the RF was 2 times of R1. Okay. We have seen Hartley oscillator. For the Hartley oscillator, the condition is tau output equal to tau input for both. So if you write for the Hartley, this is the condition to remember. Okay. This I gave you to remember this. So tau out Hartley means you have to use L and R. So it will be L2 by RF. Z input, this is tau input. So tau input will be L1 by R1. This is condition for Hartley. Now come to Colpit. For the Colpit, again the output time constant will be C2 RF C1 R1. Okay, friends. So apart from this RC, Wien, Hartley and Colpit, so this Hartley and Colpit we are using for high frequencies and this for low frequencies. So for low frequencies also we have another type of oscillator, and that is the 3-phase oscillator. Let me show you that one also. 3-phase oscillator. In the 3-phase oscillator, the circuit is, let me draw the circuit. Here R, and this is the second stage, same like this, R in parallel with capacitor. Here R, again the circuit is same, plus minus. This is capacitor, like this, the circuit is like this. See this. This is C, RF, RF, C, C, RF. This is R, R. Okay, friends. So in this case, this is the feedback part, and feedback is providing us this. So this should provide 360 degree. So this will provide you 120 degree. This will also 120 degree. And this is also 120 degree. So it's a 3-phase oscillator. In 3-phase only we are getting 360 degree or 0 degree. Is it okay, friends? Now, for this, if you'll find A beta, for this circuit, if you'll find A beta equal to 1, and if you'll do all this process, what you will get at the output, I'm telling you, okay? For 3-phase oscillator, the omega is root 3 by CRF, where is this RF is the feedback resistor, whatever we use. This is root 3. Though we have used 3-phase, so we can remember it's a root 3 phase. So this root 3 will come in numerator. Okay. So finally, if someone will ask frequency in hertz, so it will be root 3 2 pi RFC hertz. Okay, friends. So this is about frequency. But what about resistance? Resistance will be equal to 2R. This was the same condition in Wien bridge we have seen. Okay. But for RC phase shift, we were getting RF is equal to 29R. Okay. Now let's come over here. What theory part they have given? The Colpit oscillator. Wien bridge oscillator is not suited to high frequencies above 1 MHz. So the main problem is the phase shift through the amplifier. Okay, no problem. So the alternative is an LC oscillator, a circuit that can be used for frequencies between 1 MHz to 500 MHz. Very high frequency. Very high. For the very high frequency, which type of oscillators used? LC phase shift. Remember always. So the frequency range is beyond the frequency limit of most op-amps. Most op-amps are not working in this range even. Okay. So with an amplifier and LC tank circuit, with an amplifier, we have seen the diagram. In that, one amplifier we were using and one is split tank we were using. Okay. So with an amplifier and LC tank circuit, we can feedback a signal with the right amplitude and phase is feedback to sustained oscillation. To get sustained oscillation, we have to feedback properly. Shows the, I'm sorry for this. Shows the circuit of Colpit oscillator. Over here the circuit whatever we have seen. Here instead of op-amp they are using BJT circuit as the amplifier. This is our split tank. In the split tank the condition is like this. This is Z1, this is Z2, this is Z3. This part is same. And instead of op-amp they are using BJT. No problem. Now for Hartley oscillator, for Colpit oscillator, wait a minute. So for this bit, for the Colpit oscillator we have seen the condition. For both the cases the beta is minus Z1 by Z2. Perfectly fine. If beta is Z1 minus Z1 by Z2 in the case of Colpit, Z1 is C1, Z2 is C2. So the impedance of this will be 1 by SC1 and for this it will be 1 by SC2. We'll keep in this equation and finally what we get is tau output equal to tau input. Tau output is C2RF. Here C1 R1. Okay, now come to the Hartley. Now this is the Hartley, right? So this is the figure in which In the split tank, we are using 2 inductors. In the colpit, we were using 2 capacitors. Okay. So L is coming over here, so you can remember 2L. In the colpit, C is coming, so we can remember 2 capacitors. Okay. Now shows Hartley oscillator when the LC tank is resonant. The circulating current flows through L1 in series with L2. We have done this, no problem at all. So for these 2 LC oscillators, the condition is Z1 plus Z2 plus Z3 also in a loop. In a loop, if you will find, you will get this Z1 plus Z2 plus Z3. Okay. Ultimately, if I'm talking about this FR, resonant frequency, in this case, so it will be, FR is nothing but 1 by 2 pi under root 2 LC. Okay, friends. Actually, this is not the correct one. Let me derive the correct one over here. See, for the split tank we have seen, let me draw it again over here. Z3, here Z1, here Z2. Like this. Okay. So they are all are connected in series. Okay. If I'm talking about the only split tank. So the condition is Z1 plus Z2 plus Z3 equal to 0. Now we are going to derive the expression for frequency. Okay. So let's take colpit oscillator suppose. So in the colpit, Z1 is 1 by SC1, Z2 is 1 by SC2, and Z3 is SL equal to 0. Is it okay? Now can I take this S out? 1 by S, yes. 1 by C1 plus 1 by C2 plus A square L equal to 0. This will go this side, so you will be remain with 1 by C1 plus 1 by C2 plus A square L equal to 0. Is it okay? So when you will take to this side, it will become like this. So what is this? This is the C equivalent. If 2 capacitors are connected in series, so C equivalent is will be this one only. So I can take this value 1 by C equivalent, because 1 by C equivalent is nothing but 1 by C1 plus 1 by C2. Correct? So this I replace by 1 by C equivalent equal to minus of S square L. Correct? So if you take this L this side, so it will be minus L and 1 by L C equivalent. Okay. A is equal to J omega. So minus J omega square. When J square will come, minus will become 1. You will be remain with omega square. Omega square is nothing but LC equivalent. Okay. Let me take it clearly. We are getting omega square is nothing but LC equivalent. Correct? Omega equal to 1 by under root LC equivalent. In terms of frequency, if I'll talk about, it will be 2 pi L C equivalent hertz. So this is the frequency. So for the colpit we are getting C equivalent. For the Hartley we'll get the same. We'll get the same, and the frequency will be 1 by 2 pi. Here now L equivalent will be there, and this is the C. This is the resonance frequency for the LC oscillators. Okay. For Hartley, and here for colpit. We'll discuss one by one now. In the Hartley, the condition is T out should be equal to T in. T out will be L2 by RF. Here it will be L1 by R1. This is one condition. If you'll talk about the resonant frequency FR, it will be 2 pi C into L equivalent. Okay, friends. Now come to the Culprit. Here also tau out is equal to tau in. So tau out is C2 into RF equal to C1 R1. So FR is nothing but 1 by 2 pi C equivalent into L. This is okay, easy to remember. Okay, friends. So let me correct this. This is not 2LC, this is something. Yes, for Hartley, yes. L equivalent for the Hartley is 2LC, correct. This formula is absolutely correct. L equivalent for Hartley will be L plus L. If both are same, it will be 2L. Yeah, correct. But you have to remember the generalized formula, and generalized formula is FR equal to 1 by 2 pi L equivalent into C. And if you have Colpit oscillator, so same formula will be 1 by 2 L C equivalent. Okay. Now we'll see some problems based on this. This is one of the gate problems, and the problem is given. The circuit is very complicated over here, but it is 30 seconds only answer. If you want to answer this question, it will take 30 seconds. But to draw this circuit, it will take 45 seconds for me. Okay, no problem at all. This is over here, something like this. It's like this over here. I think you identify which of the oscillator is given over here. LC minus VC. I'm not giving you value, otherwise you will solve before me. Okay. I'll give you values after drawing this. RE is given over here. Over here, CE. This is grounded. And this is connected over here. Everything is given. Everything, the perfect circuit. The oscillator circuit shown in the figure is given like this. Now you have 4 options, and the option A is given. This is Hartley oscillator, and the frequency of oscillation is 79.6 megahertz. Option B is given, it's Colpit oscillator. Frequency is given 50 megahertz. Option C, Hartley oscillator with 159 megahertz. And option D is CO with 159.2 megahertz. These are the options. So for this question, easily you can identify this is Colpit. Why? Because 2 capacitors are using, and each capacitor value is 2 picofarad, 2 picofarad. Okay. They are asking, So for this question, they are asking frequency of oscillation. This is the 2-mark question, 2001 gate. Once you identify, or you have find out this is the Colpit oscillator, the frequency of oscillation is it given in hertz? Yeah, this one is given in the hertz only. So it is 2 pi under root. L is given 10 micro. Okay, perfectly fine. C equivalent. What is the C equivalent of this 2? Definitely it will be 1 picofarad. 2 into 2 divided by 2 plus 2. So this is 1 picofarad. 1 10 to the power minus 12. So finally you have FR equal to 1 by 2 pi under root of 10 into 10 to the power minus 18. Okay. So if we'll calculate this, so this will be, if we'll calculate, it will be 50.3 megahertz. So option B is correct with CO, Colpit oscillator. Is it okay, friends? So So if in examination the question will come from this background, so it will be like this, a big circuit, and it will take only 30 seconds to calculate the answer. Okay friends, so please remember all these parts thoroughly. What is the Colpite oscillator? What is the LC oscillator? These are the all formula based. Till now we have seen RC phase shift, three phase oscillator, Wien bridge oscillator, Hartley and Colpite. Means we have 5 oscillators. Colpite and Hartley oscillators, these are the high frequency oscillators, 500 megahertz, right? And for the high frequency we use only LC oscillators, Hartley and Colpite. Now for the lower frequencies we can use 3 oscillators. The first one is RC phase shift, second is 3 phase, and the last one is Wien bridge. Okay, which one of the following, the question is, suppose the 1 mark question, which one of the following oscillators are used for the audio range frequency measurement? We have 4 options given: RC phase shift, 3 phase, Hartley and Wien bridge. So Wien bridge is the answer for that. Okay, so we'll consider one more problem and then we'll bind up this session. Okay, so the circuit is given. This is kind of forward circuit, and this is the feedback circuit in which we have RC circuit. This is the RC circuit given over here. These 3 are grounded. Let's take it R, C, C, C. Perfectly fine. Now the question is, the oscillator circuit shown in the figure has an ideal inverting amplifier. Okay. Its frequency of oscillation in hertz is. Frequency of oscillation in hertz is, they are asking. Okay. Now they have given the 4 options. This is the question of 2 seconds. The first option is given 2 pi under root 6 RC. Option B is given 1 by 2 pi RC. Option C is given 1 by root 6 RC. And the last one is, D option is given 2 pi RC under root 6. So what is the difference in first and second? 2 pi RC, 2 pi RC. Both are same. Is there any difference between A and D? 2 pi RC root 6. There is no difference. So let's take it something else. Let's take it root. Okay. So friends, this is simple. RC phase shift. They're asking. This is the 2 marks question, 2003 gate 2 marks question and 2 second question also. Why 2 second? Because we know already the frequency of oscillation is 1 by 2 pi RC under root 6. This is the RC phase shift. And I gave you short trick to remember this also. This is like this and make it 6. Is it okay, friends? So this is the question. Very easy question. So you have to remember the formulas for all this. So let me tell you for this 3 things: RC, 3 phase and Wien bridge. For the RC, the formula is frequency formula 2 pi RC root 6. For 3 phase, this root 3 phase, root 3 will come over here. It will be 2 pi RC. For Wien bridge, it's very simple, 2 pi RC only. Okay. In this case, RF was 29 times of R. In this case, RF was 2 times of R. In the Wien also, RF was 2 times of R. Is it okay? So I hope this is clear to you. Now I'll see the last question of the day, and the question is very simple. 1 mark question, 2015 question. Sorry, 2 marks question. V naught, over here R1, R2, and this is 2C, this is R, here C, this is 2R. So, it's a Venn bridge, clearly seen. Venn bridge is given over here, and the question is, the circuit shown in the figure has an ideal op-amp. The oscillation frequency and the condition to sustain the oscillation respectively are, your options are given, 1 by CR, this is the frequency, and the condition is R1 should be equal to R2. The option B is given, 1 by CR and R1 equal to 4R2. Option C is also given, and that is 1 by 2CR and R1 equal to R2. Option D is given, 1 by 2CR and R1 equal to 4R2. Okay friends, these are the options you have given. So, in the Venn bridge, we have seen the frequency is 1 by 2 pi RC. Is it okay? But this is the condition when R and C is given. But here it's given 2C, here it's given 2R. So if I'll talk about the time constant of this branch, the time constant initially RC, but this time it becomes 2RC. Similar thing is going to over here also. See, here also time constant is doubled. And this is the frequency. Which frequency they are asking? Radian per second or something? Yeah, this is radian per second. Okay. So let's take omega equal to 1 by RC. So see friends, time constant is doubled. Time constant is double. So definitely your frequency will be halved. Okay. Because frequency is inversely proportional to the time constant. Here time constant is double, so frequency will be halved. So this is the frequency for Venn bridge, but for this bridge given omega equal to half of the previous one. So it is half of 2RC. Now we have two options like here. Now in the Venn bridge, the condition of R1 and R2 relation, this is R1 given over here. Yeah, this is R1, this is R2. The relation was RF equal to 2R1. So here time constant is double, so here also the same thing will happen. So this condition will become now R1 equal to 2R2 according to this bridge I am giving. Oh sorry, 4. 2 is already, it will also doubled. So this is the 4. So this is the option. So dear friends, this is all about of today's class. We'll meet in the next class and we'll start the power amplifier. Okay? Okay. We'll meet in the next. Bye.